Hi all. Hi folks. In this lecture, I will be talking about the simplest model in inventory management, which is called economic order quantity model. Okay, let's take a look at what economic order quantity model says. Okay, in economic quantity order model, we are going to use letter Q as an order quantity or lot size, and we will try to determine the optimal amount of order size that a company should give for a typical SKU to minimize total annual inventory holding and ordering costs. Remember what holding cost is? Holding cost is about unit cost of holding one unit in your storage area, which is related to insurance cost, storage cost, labor cost, energy cost, and so on. And ordering cost is the cost of giving one order, which includes a phone cost, labor cost in your purchasing department, documenting cost, inspection cost, and so on. In the simplest model, we do have five assumptions. Five assumptions. These assumptions should be true to be able to use EOQ model. First, we know the demand. The demand is known and it is constant. It doesn't change over time. Okay, it's 100% known, 100% certain. Okay, for instance, a chocolate bar is demanded 100 units every week. Okay, every week we get an order with 100 units of chocolate bar. Okay, it doesn't change over time, and there is no constraints in the lot size. Okay, the supplier doesn't limit our lot sizes. If we would like to order 101 units of chocolate bars, they can supply it. Okay, there is no constraints on it, and also only the type of cost we consider to minimize are holding cost and ordering cost. Okay, and then the fourth assumption is about this. We are going to make a decision one time every cycle, and which is independent from all other SKUs. Okay, there is no relationship between SKUs. SKU A is going to be ordered once every cycle, which is not related to any other SKUs. And the last one is we know the lead time. Lead time is the time we receive our order after we give it. Okay, it is constant and it is known. If it is 1 week, it's always 1 week. If it is 3 weeks, it's always 3 weeks. Okay, and in the simplest one, we are going to first assume that it's going to be zero. Okay, so before I start to discuss the model, I would like to highlight that. Remember from process strategies courses, we had several production strategies such as make to order, assemble to order, make to stock storage strategies. EOQ could be applied if you apply make to stock strategies. Okay, if you apply make to order strategies, you cannot use EOQ because order size is constrained in make to order strategy, right? You produce according to your customer orders, right? One wedding dress or 10 shoes. Okay, and if there is a quantity discounts, you can easily modify EOQ, but I'm not going to discuss the modified EOQ model with respect to quantity discounts or production amount and so on in this course. These are advanced models. I will leave it for as elective course. And also the EOQ is valid if the setup costs and order costs are known and stable, which is one of the assumptions in EOQ. EOQ model has this kind of zigzagging shape, which is a soul sieving shape, okay? And in this shape, the y-axis shows on-hand inventory, and at the beginning of the cycle, we do have Q units of inventory on hand, and then as soon as we receive order, remember the demand is constant, and known, okay? So the amount of on-hand inventory reduces with this linear slope. And by the way, which this slope is determined by demand, okay? And then as soon as the order, the amount of on-hand inventory goes to zero, we receive our next order immediately. Immediately we receive our next order. So we never have stock out. So the amount of inventory on hand never goes below. Okay. So therefore, the next question will be related to where we should give an order. Okay. For that purpose, we are going to define a reorder point. Reorder point will define where we need to give our next order. And as we discussed before, at the beginning we do have Q amount of units at the cycle. At the end of cycle, we do have zero amount of units. So the average inventory, which is cycle inventory, remember, is Q over 2. This is the time between orders. Time between orders, which shows or the length of cycle. Okay. So we said that we would like to minimize annual holding, total annual holding, and total annual ordering cost. Annual holding cost could be easily calculated by average cycle inventory, which is Q over 2, times unit holding cost. Unit holding cost will be determined by letter capital H. Annual ordering cost is related to how many orders you give in a year, in a year, and multiplied by one ordering cost or cost of giving one order. Okay, this is going to be represented by K and A's. And then total annual cycle inventory cost, which is the sum of these annual holding costs. Let's take a look at how they are going to be represented and calculated. Okay, so holding cost is a linear function because Q over 2 divided by H. H is fixed, so it increases with Q. And ordering cost is K times S, okay? K is depending on Q and demand. I'm going to show in the next slide. So it is not linear. However, it decreases as the amount of Q increases. Let me just give an example. If the annual demand is 1,000 units, okay, if the annual demand is 1,000 units, and then suppose that the amount of the order quantity is 100 units. So every time you give an order, you give the order size is 100 units. How many orders we give in this case? We give 10 orders, right? We give only 10 orders. And the cycle, the cost of holding cost will be related to our cycle inventory, right? And then when you change Q to 200, okay, how many orders we will give? 5 orders we will give, and it will be multiplied by ordering cost, and then we will calculate total setup cost or ordering cost. So as I just said, Q over 2 is a cycle inventory, H is the holding cost, holding cost per unit per year. If the holding cost is not given, you can simply take it as a cost of capital. To calculate the cost of capital, you can use annual interest rate and unit cost of the item. Okay, but pay attention, because demand is annual demand, you have to have annual holding cost rate, or you have to use annual interest rate to calculate holding cost per unit per year. Okay, S is ordering cost. D over Q, I just mentioned that K, okay, D over Q. D over Q gives us the number of orders given in a year. So that's why the ordering cost function is not linear, because of 1 over Q, okay, in this formula. So let's solve an example problem. There is a museum which operates 52 weeks per year. The top selling SKU, only one SKU, which is one of the assumption of EOQ, bird feeder. Okay, sales are demand is 18 units per week, which is constant, and the price of the good is $60 per unit. Ordering cost is, which is S. Okay, setup cost is $45 per every order. Annual holding cost is 25% of feeder's value. In this case, you can suppose that this is I, okay, and feeder's value is its price, okay, and then already the company chose 390 as a unit lot size, and they are asking what is the annual cycle inventory cost if this is the ordering quantity, and then what happens to total annual cycle cost if the ordering quantity is 468. Let's go ahead and calculate each term and then total cost. D is, remember, we need to consider annual demand. This is weekly demand. There are 52 weeks, so this is the annual demand. And H is holding cost of holding 1 unit per year. And this is the holding cost rate, which is given in the question. If it is not given, we can easily take interest rate as a cost of capital. And they said that we have to take 20% of the price of the good, price of the product, which is $60. So holding cost is $15 per unit per year. So cycle inventory is this in the first policy because their current ordering quantity is 390. And then when we multiply these two terms, we get the total inventory cost according to holding and ordering cost is this. When they change order quantity to 468, let's see what happens. Total inventory cost increases from 3,000 to 3,600. Because of what? Because of holding cost. Because now we are holding more units in our inventory because of the cycle inventory increased. Even though the setup cost, order cost decreased, right? Because because we are giving higher amount of orders, we give a less amount of orders before. The quantity increases, the number of orders given decreases. Okay, therefore, cycle inventory increases, ordering cost decreases. However, because holding cost is more important than the ordering cost in this example, or critical than ordering cost, total cost increases. Okay. So this is the plot of the total cost in this example. And what do we see? We see that total cost first is very high because lot size is very small, okay, due to cycle inventory. And then it decreases up to some point. And then it starts to increases. So remember at the beginning of the lecture, I told you that we need to minimize total annual holding and ordering cost. So where it is minimized is somewhere right here. So this point will be called economic order quantity, optimal economic order quantity. How can we calculate optimal economic order quantity? By using this formula. If we take the first derivation of the total annual holding and ordering cost, we can get this formula. Okay, D is annual demand, S is setup cost, H is holding cost. And how about time between order for a given ordering quantity? Q over D is the time between order. When you multiply this by 12 months, you can calculate in terms of months. So Q over D is time between order. D over Q is number of orders we give in a year. Let's go ahead and solve an example problem. In the previous example, we knew that this is the demand 936, which is the ordering cost. So the optimal amount of order should be 75 units. If we give in our orders in 75 units, so the lot size is 75, then the total annual holding and ordering cost will be minimized. Okay, so what is the time between each order? This is the demand. This is the optimal order quantity. So every 0.08 year, we give order. In terms of months, every 1 month, almost every 1 month, we need to give an order. Every 4.2 weeks or every 29 days. Okay. So this is another example problem. Okay, reviewing the inventory policies on an $8 item stock at a hardware warehouse. The current policy is to replenish inventory by ordering in lots. This is the current Q. This is the current Q. This is the price of item. Okay, so demand is given 60 units per week. So in terms of years, this is the annual demand. S is $30 per order. Holding cost rate is defined as 25% of the selling price. Selling price is 80 units. So either you can, after you multiply these two terms, you can easily get H is 20. Okay, so the optimal EOQ after you do this calculation, it will be 9 units. Remember, this should be annual demand, and this is the annual holding cost. So in the current policy, their Q was 300 units. When you calculate cost, this is the average inventory Q over 2. This is holding cost, and this is demand. This is Q. It gives us number of orders in a year, and this is setup cost. As a result, the total annual holding and ordering cost is this. In the optimal policy, Q is this, and the total cost is this, almost half of this one. Okay, and how about time between order? And this is Q, this is demand. Okay, and 6 weeks. Every 6 weeks we are going to give one orders. I'm sorry, in the current policy they were giving one order every 6 weeks, but because the lot size decreased from 300 to 92, in the optimal policy we have to give one order every 1.6 weeks. Okay, so let's take a look at the effects of the change in parameters on the lot size. If demand increases, you can simply see that this is equal to Q, right? Q will increase. Q will increase with a proportion to the square of demand, right? So if annual demand increases, the lot size is expected to increase. If the setup cost increases, so if giving an order becomes more costly, okay, then you would like to give orders in larger amounts. That is also one of the reasons of keeping large inventories we discussed at the beginning of this chapter. Okay, if holding cost decreases, then you would like to again keep more inventories. Therefore, Q increases because it is cheaper to keep inventory than before. Then why shouldn't I keep more inventory and reduce the number of orders give in a year, right? Okay, this is the end of EOQ model. In the next lecture, I will be talking about inventory control systems. And remember, in the EOQ model, one of the assumptions is demand is constant known. However, in practice, it is not always true. I will relax one of these assumptions and show you one of the more, not, yeah, one of the more advanced models. Have a nice day. Take care.